Good afternoon. It's my pleasure to welcome all of you for today's colloquium. Today we have two very special guests, Professor Jean Surdej and Anna Ospijaska. I'm sorry if my pronunciation is not close to the way you pronounce it. Okay, so Professor Surdej does not require any introduction to the astronomy community. He has contributed enormously in the field of astronomy and astrophysics, in particularly on astronomical instrumentation. Nevertheless, for the sake of general audience, let me introduce today's speaker. Professor Jean Surdej has followed a career under the Belgium National Fund for Scientific Research. He has also been a staff of astronomer at European Southern Observatory ESO La Silla, Chile between 1976-78, ESO Geneva 1978-80, ESO Munich 1983-85, and at the Space Telescope Science Institute, Baltimore between 1993 and 1996. In 1995, he obtained the title of FNRS Research Director. In 2002, he switched to an academic career path. In 2007, a visiting professor at University Adam Mickiewicz, Poland, and very distinguished VAJRA adjunct faculty at ARIES Nainital. Since October 2017, he is also involved in research, teaching, formation activities abroad, in particular Qatar, India, Chile, and Poland. His main astrophysical field of interest are radiative transfer in expanding atmospheres, asteroids, quasars, gravitational lensing, telescopes, and optical interferometry. So we welcome Professor Jean Surdej for today's colloquium, and I guess it will be an sort of exciting experience for all of us. Before we start, let me also share that Professor Surdej is visiting IST between 2 to 4th April. So any student or faculty member are free to interact and sort of spend times with him, and he's sitting next to director's office. Thank you and welcome to Professor Surdej for colloquium.
Okay, thank you so much for this introduction. So, well, it's a pleasure to be here. We've been here with my wife 10 years ago, exactly, yeah. And we had no rain, so well, we enjoy the warm rain here, yeah. So, I'm going to talk to you about observing the wonders of nature from camera obscura to the 4-meter ILMT. But generally speaking, yeah, I think some of you have been struck here by the nice examples of that nature offers us, you know, to understand the physical principles. Like, for instance, well, when you look at the rainbow, yeah, it gives you an idea of how a spectrograph works, yeah. When you look at the bubbles in the sea, you know, like some bubbles, yeah, it gives you a good introduction to understand, you know, how a Fabry-Perot interferometer works, yeah. And today I'm going to show you, yeah, how nature has invented already before us, yeah, the photographic camera. Not only photographic camera, but also theorem of convolution. Also, well, the conic, you know, trajectories. So this is the aim of my presentation today. Now, well, in the ILMT project, yeah, which started, in fact, in 1997, so a long time ago, many people have been involved, yeah. And here I just want to show you that this is the the result of a joint effort of many people, not a single person at all. And well, in particular today, Kuntal Mishra, who is heading the project at ARIES in Nainital. And also we receive a lot of support here from Professor Paul Hickson in Vancouver, who has been a pioneer in developing the technology that has made possible the 4-meter liquid mirror telescope. But of course, there are many more contributors to the projects that I don't want to list all here. But since it has lasted here for so many years, because there have been many obstacles, especially administrative obstacles, all that took a long time. Now, well, I always have the pleasure to show this slide, which represents the Earth that you see here, in front of its host star. Well, nice illustration of our insignificance. And you just remember that Earth is immensely small compared to its host star, and this should incite all the men to some humility, modesty, especially to peace on Earth, which is under threat, and well, in several countries of our world, unfortunately. Now, the concept of a liquid mirror telescope dates back in the 17th century, when Newton already knew that if you set a liquid in a cylindrical recipient that is in rotation around its vertical axis, it would take the perfect shape of a paraboloid. And then it was Ernesto Capocci, who was the director of Naples Observatory, who had the idea of using mercury as a reflecting liquid. Well, then you see, well, we have to wait the end of the 19th century for Henry Ski, when it was in New Zealand, who constructed a 35-centimeter mercury mirror prototype, but just in the lab, so he didn't try under the sky. Robert Wood from Baltimore designed a 51-centimeter prototype mirror telescope that he used under the sky. But he noticed the difficulties of getting clear images of the stars due to the transmission of the vibrations of the ground, and also given the difficulty of keeping constant and uniform the rotation of the mirror. Well, it was in 1982 that Hermano Borra, who is also a member of our collaboration, had the idea of using a hair bearing to fix the cylindric recipient on it, so that you would avoid transmission of vibrations. And well, he also suggested to give a preform to your mirror by pouring a liquid resin in it, letting the ball spinning. Then the resin would get solidified and take an approximate shape of a paraboloid. This would enable you to use a much thinner layer of mercury, which would make the weight much less on the support. The first really good prototype of a 2.7-meter liquid mirror telescope was built in Vancouver by Hermano Borra and Professor Paul Hickson. So you see, we already entered the game many years ago. And Paul Hickson was also involved in the NASA Orbital Debris Observatory, which was a 3-meter mirror used for space debris detection. Then Paul Hickson alone constructed in his backyard a 6-meter liquid mirror telescope known as a LZT telescope, and it was not used for astronomical applications because he had no specific corrector, neither a good CCD camera, and furthermore the site of Vancouver is the worst place in the world you may think to do astronomy. Now, well, this slide shows you a view of the 2.7-meter UBC Laval mirror telescope. This is a 3-meter NODO, so used by NASA for space debris detection. Here is a 3.7-meter Laval mirror used in the laboratory only. And here, the 6-meter LZT by Paul Hickson that has been used for LIDAR applications. Now, well, in our case, yeah, our first contact, yeah, with liquid mirror telescope dates back in 1996. And one of our contacted me and asked, well, would such a telescope be of any use to observe gravitational lenses? And my response was very clear. I said, no, not at all, because at that time, about only 10 gravitational lens systems were known. And the probability that, you know, the telescope would be properly oriented, yeah, in the direction of one of these, yeah, was very, very unlikely. Yeah. Well, then he insisted in 1997, he organized a conference in Marseille, France, and with one of my PhD students, Jean-François Claskens, we thought, well, in the field of view of the telescope, yeah, we would observe about 20,000 quasars. And among 20,000 quasars, you would expect, well, on the average, 20 gravitational lens systems, which means that, well, it would be a very, very good case, yeah, to use a liquid mirror, because every night, yeah, you could observe, well, at least a fraction of these. Then in 2007, well, an interesting meeting took place in Liege, while Professor Ramsagar was at that time the director of ARIES, yeah, visited Liege to purchase, yeah, the DOT, the Devasal Optical Telescope 3.6 meter that has been fabricated by the company Amos in Liege. And well, we were put into contact and we had a discussion about, I mean, the interest that we would have to install our liquid mirror telescope in India. And well, my first answer was that this telescope here uses a very specific corrector, which is latitude dependent. And it was designed to be installed in Chile at a latitude of minus 29 degrees 30 arc minutes. So I said, well, there is a problem with the latitude. But what is the latitude of Devasal? And the latitude is plus 29 degrees 20 arc minutes. Yeah? Just fit, yeah, to well, shift by 180 degrees, yeah, that corrector, yeah, that could be used. So we decided that probably fruitful interactions between Indian and Belgian astronomers would also arise, yeah, from such a collaboration. And this is how the project started here in India. Well, I like to project this slide because it's one of my preferred paintings, yeah, Bal du Moulin de la Galette, that you could see in Paris, yeah, by Pierre-Auguste Renoir. And when he showed that painting, yeah, the critics was very negative. They say, wow, it's a very imperfect, you know, well, you see all kind of spots of light on your painting, yeah, which makes it, you know, well, not really acceptable. And Auguste Renoir, yeah, lived, well, very modestly, yeah, and could not earn his living out of the paintings. Today, the value of that painting is estimated to 127.4 million US dollars, yeah. So, poor Auguste Renoir. Now, well, regarding those spots of light, yeah, well, it's amazing to see that, well, on the ground here, some we recognize, yeah, the building at Ayuka, yeah, that you see those spots of light. Here's the same on the wall, vertical wall, yeah, in Poznań in Poland, yeah. And of course, yeah, well, camera obscura, yeah, is a secret answer, yeah, to the formation of those spots of lights. So, well, the best camera obscura that you could make, yeah, is to use a tube, yeah, of a poster, and to set an aluminum foil at one hand with a small hole, and at the other end some butter paper, and then you direct it in the direction of the sun, yeah, and you will see, of course, yeah, image of the sun. So here is another model. So if you would look at a candle, you know, at a very far distance, what we would see is, of course, the top of the flame at the bottom, yeah, of the butter paper on the right side, and the bottom of the candle, yeah, at the top. Yeah? So just reverse image. Everybody knows that, yeah? Now, let's assume that you direct, yeah, your pinhole camera in the direction of the sun. What you will see, of course, yeah, is an inverted image, yeah, of the sun. Now, it's important to know that the angle under which you see the solar disk, yeah, in radian is 1 divided by 114. Yeah? The reason is that if you would like to hide, yeah, the solar disk with your thumb, which measures about 1 centimeter, you would have to put it at a distance of 114 centimeter. Yeah? So 1/114 is a tangent of the angle under which you see the sun, solar disk. Yeah? But since the angle is small, it is its value in radian. Now a question for the students. Let's assume that the length of your pinhole camera is 114 centimeter. What would be the linear diameter of the projected sun on the butter paper? Does anyone know? How much? 1 centimeter. Of course, 1 centimeter, because here too we see that the angle is 1 divided by 114, absolutely. Now, as you know, in the foliage of the trees, yeah, you have many leaves, and between the leaves, yeah, you have formation of holes. And through the holes, yeah, the sunlight rays pass and project on the ground, yeah, those nice solar disks that I showed before, which were the spots of light that you could see, yeah, in the painting of that I showed before. Yeah. Now, same question. Well, the angle under which, yeah, well, the hole in the tree sees the solar disk is 1/114, which means that if the solar disk you see here on the ground measures, well, as a linear dimension of 5 centimeter, you may estimate, of course, yeah, the distance between the solar disk and the hole in the foliage of the tree. Yeah, you multiply 5 by 114, and you find 5,7 meter. Yeah. So this is a nice activity for public outreach, yeah, especially to let the young pupils know that they may measure the height of a tree, which is absolutely dedicated to Kerala, because the sun gets very high, almost near the zenith. Yeah, so you just wait the sun to be near the zenith. You look at the solar disk projected on the ground, and you get immediately an estimate, yeah, of the height of the holes in the trees. Yeah. Okay, now formation of solar disk and convolution theorem. Yeah. So here a few more examples of those solar disks, yeah, which you may see frequently. Now a small video. Well, here you see as a function of time, yeah, the formation of those solar disks, yeah, when it's windy, yeah, because when the leaves are moving and the holes, yeah, are being produced, being destroyed, yeah, and you see the disappearance of those solar disks, yeah. Then what you would also tell the young pupils, yeah, is that, well, if they set the shadow, yeah, of their head on the solar disk, yeah, well, you will directly see, yeah, the hole in the tree, as a flash of light, yeah, because, well, the sun, yeah, will appear, and it's nice to know that you may see this flash of light as shown on this picture. Yeah. Now you may also produce, yeah, those solar disks, yeah, with your fingers. Yeah, just try to make very, very small holes between your fingers, and you project the light, yeah, on the wall. Well, here you would project on the ground because the sun is very high, yeah, in the sky. Now I come back to the camera obscura, yeah, to get an introduction to the telescope. Yeah. So we agree that if the candle is very far away, yeah, you get a first inverted image of the candle, but through the second hole, you get a second image of the candle, which is exactly translated, yeah, by the distance separating the two holes. Yeah, so it's a mere translation. Same for the third hole. Now, if you set, yeah, okay, now instead of a candle, I use a heart, yeah, colored heart. So it's a source of light that I set at a very large distance, you know, as if it would be at the sun distance. And then I see that, okay, as the holes get closer, yeah, well, the images get blurred, yeah. If I set the holes still closer, well, they still get more blurred, yeah. So in summary, we see that, of course, I mean, first of all, yeah, closer are the holes, yeah, more blurred are the images, and in a moment we will see that farther away is a butter paper, yeah, from the holes, yeah, fainter the sources will get to. Yeah. So this is what is shown here. So here, the hole, the pinhole, yeah, consists of many holes, okay? And we see that if you set the screen, yeah, very close to the holes, well, it's blurred images. If I get farther away, yeah, the images get less blurred, yeah, still farther away, less. And that the blurred is certainly proportional, yeah, to the surface area of the combined holes, yeah. So d square, yeah, and h square, sorry, and inversely proportional, yeah, to the square of the distance, yeah. Now, regarding the surface brightness, well, it's easy, yeah, to agree that the surface brightness will be proportional, yeah, to the square of the holes because you let more light entering your pinhole box, yeah. But inversely proportional, yeah, to the square of the distance because I mean of a geometric dilution, of course, yeah. So you have one advantage, yeah, in using the small holes, but you get the disadvantage that the images get much fainter. Now I have a quiz, so be very present. The hole is a heart, and my source of light is the sun. And I set the sun, yeah, very far away, yeah, at the distance of the sun. And now I will be looking with the screen, yeah, at different distances. Yeah? So what shall I see? Shall I see a heart, blue, yellow, inverted? Or shall I see a sun? Oh, I already showed the answer, yeah? So, okay, the answer is I will see a heart, yellow, well, in the same orientation, yeah? Okay? Now, but now, if I set my screen very far away, yeah? Shall I see a heart, yellow, blue, or a sun, yellow, blue, inverted or non-inverted, yeah? Who is in favor of a heart? Yeah. No one likes the hearts here, yeah? Yeah. So who are in favor of a sun, solar disk? 2, 3, 4. Yeah, a small majority. Yeah, okay. Inverted or not inverted? No? Yes, it will be inverted. Yeah. You agree because the rays going up, well, coming from the left side, yeah, which are up, will end up, you know, in the lower part on the right side. Yeah. Okay. And now, before falling asleep tonight, yeah, this is the kind of exercise, yeah, I like practicing, you know, every day, yeah. It's just to try to understand why at an intermediate distance, but even if it is very close or very far, yeah, the image that you see, yeah. So the image that you see, yeah, is just a convolution product, yeah, of the shape of the art or of the holes, yeah, by the image of the sun that would be produced if your hole would be infinitely small. Yeah. Now, well, a way to really understand it is that you say, okay, if I have a hole, I may consider it as made, yeah, of infinity of small holes. Yeah. So the first small hole will give me a solar disk, yeah, which is very faint but very clear. Yeah. No fuzz. Yeah. Now, if I take another small hole, yeah, which is part of the big holes, yeah, well, the image will simply be translated, as I said before, yeah, by the distance between the two holes. Yeah? It's really what you see here, yeah. Or you could make it the other way. You could say, okay, it's as if I would take, yeah, just one single image of the sun, which is perfect at a certain distance, and this is made by one hole. But as I have a well infinity of the holes, well, I would just come at the level of the projected solar disk image, yeah, and move it around and integrate, yeah. So you would see, well, this difference in coordinates, you can set it here or there, it's the same, yeah. It doesn't affect the convolution product, yeah. This is a nice property, yeah. So before falling asleep, yeah, just think about that, yeah. It's fun. So it's very simple, yeah. Okay, now what I want to show you is a very nice experiment to be made, yeah. It's just to take a piece of cardboard, yeah, and just make some holes in different shapes. So you see an ellipse, a star, a square, circle, more or less, in different dimensions. Well, here are just 3 squares. And then you just take a A4 sheet of paper, come very close to it, and what you see, indeed, if you're very close, you see the images of the holes, yeah, perfectly. If you go further away, well, you see the blur is coming into play. If we still go further away, well, you see there is a passing cloud, yeah, in front of the sun, which is seen in all images, yeah. And if you still go further away, yeah, well, this is fantastic. You only see, yeah, perfect solar disk, almost, yeah, yeah. But this was the smallest hole, and you see it is the faintest image that you get, of course, yeah. Well, here in Kerala, instead of putting this on your window, as I did here in Liege at latitude plus 52 degrees, you would rather set, yeah, the screen, you know, horizontally, in a horizontal position with respect to the sun, yeah. But it's fun doing this experiment. Okay, and now, well, and what happens if the diameter of the hole gets infinitely small? Do you get an infinitely clear image of the sun? Of course, no, because of the diffraction effects, yeah? And if in addition you have seen, yeah, it makes things worse, of course. Okay, now, well, basic principles of a telescope, yeah, from the camera Obscura is as follows. I take back the candle, put it at a very far distance, yeah, from the pinhole camera, and I know that you get a first inverted image. Now for the second hole, what you would like to get, yeah, is not a candle image, yeah, well, at that location, but just superimposing the first one, yeah. So what you would do, yeah, just make use of a prism, small prism of light that will deflect the light ray, yeah, to the bottom, yeah, like this one. You see, it's a small prism, and of course, yeah, the light ray, yeah, will go in that direction. Do you do the same for the bottom hole? Yeah. And what you are constructing converging lens. Yeah. And so this is what a telescope is about. Yeah. It's just a converging lens. And then you have the focal plane here. And here you would come with a eyepiece, yeah, or magnifier, and would look, yeah, on the butter paper, your image, or you could set also, yeah, well, CCD detector or photographic plate. Yeah. Okay, now what about using reflective material? Well, we know that if we use a flat mirror, where the light rays then coming from a distant star will go back to the distant star, yeah? And so astronomers would be very unhappy, yeah? So what we would like to do is just to curve the mirror, yeah, of course. And what's fantastic is that when you're curving the mirror, what you would find out is that the only shape which gives you, well, all rays and converging into a single point is a paraboloid shape, yeah? And furthermore, yeah, what's fantastic is that the length of each of these rays, yeah, from the star to the focal plane, well, yeah, to the focal image in this case, yeah, are the same, yeah? So the length of that ray going here, or of that ray coming here, are exactly the same. And therefore, you get a diffraction image, yeah, which is a Airy point spread function, yeah, and which defines, yeah, the angular resolution of your mirror if you would set it in space, yeah. Of course, on the ground, you would be limited, yeah, by the atmospheric scene. Okay, as I told before, yeah, Newton, yeah, well knew that if you set a liquid in a rotating dish around this vertical axis, yeah, it will take naturally the shape of a paraboloid, yeah. And the focal length, as I show in a moment, yeah, can be easily derived, is just proportional to the gravity and inversely proportional to twice the square of the angular velocity of your mirror. So for the students, yeah, I will show you the way of establishing that relation. So let's assume, yeah, that you have a liquid in rotation, yeah, or first not in rotation, yeah. There is no rotation, so the only acceleration acting, yeah, on the liquid is gravity. So the liquid will set perpendicularly, yeah, to the net acceleration it experiences. Since the gravity, yeah, is directed towards the center of the Earth, yeah, well, the water, yeah, gets flat, horizontally flat. Now, in the case of a liquid, yeah, which is spinning inside a cylindrical container, Well, in addition, yeah, so we would like to know what is the equation of the shape, yeah. In addition to the gravity, yeah, you have the centrifugal force, yeah, centrifugal acceleration. Yeah. So here I have represented here the net acceleration composed of the gravity, which vectorially is added here to the centrifugal force, which is proportional to the square of the angular velocity into the distance, yeah, from the optical axis, x, yeah. So what we may write, yeah, or we can see directly that if you draw the tangent, yeah, to the surface you are looking for, yeah, you see that this angle is exactly equal to the angle between the net acceleration and the gravity orientation. But since the gravity is perpendicular, yeah, to the horizontal axis, and the net acceleration perpendicular to the tangent, yeah, where the two angles are the same, and so the tangent of this angle is, of course, omega square x divided by g. So this is, of course, the slope of the tangent, dy dx, equal to the ratio of omega square x divided by g. So integration here is straightforward. Yeah, you find that y, yeah, is simply omega square over g, which are constant, multiplied by x squared divided by 2. And well, in the case of the equation of parabola, yeah, uh, where you have defined the focal length, the equation is the following one. Yeah. So what you do, you identify, yeah, this constant to that one, and you find the expression of the focal length, which is g divided by 2 omega squared. Yeah. Which means that faster, yeah, your mirror will spin, yeah, shorter will be its focal length. Yeah. So this is what is shown on this diagram. You see a mirror which is slowly spinning. Well, when there is no rotation, when focal length is infinitely long, and faster it's spinning, yeah, shorter becomes the focal length. Yeah. Now, well, the difficulty, yeah, well, of course, I mean, these telescopes are diffraction limited, as I said before, yeah. Now, there is a difficulty, yeah. Your telescope, yeah, since it's spinning around a fixed vertical axis, yeah, cannot be oriented, yeah. So during the time you are observing, yeah, the Earth is rotating and the stars are passing the field of view. Now the question is that, well, what is the trajectory followed by the stars in the focal plane, yeah? Now to find the answer to that question, yeah, well, let's look at the sun, yeah? During the day, the sun, yeah, makes a circle where the center, yeah, is exactly the location of the northern star, yeah? Okay. And now the light rays from the sun, do you agree that they are sweeping, yeah, the surface of a cone? Yeah, because well, yeah, the light rays, yeah, follow the circle. Yeah, so the light rays, yeah, sweep the surface of a cone. Yeah. Now those light rays enter your optical system, so it's still a cone of light that you intersect with a flat surface, which is a detector. Yeah, CCD detector. Yeah. So what is the trajectory? It's a conic. It's a conic. Yeah. And the conic can be anything. It can be, well, a parabola, branch of hyperbola, a circle, a straight line. Well, for instance, if you would be at the equator, yeah, and would look at the sun, yeah, when on 21st of March, yeah, well, the sun, yeah, would remain in a plane, yeah, in the equatorial plane, and well, its rays, yeah, would just well project on the ground, yeah, shadows which are straight lines, yeah. Now, in the case of the liquid mirror telescope, the intersection of the cone of the stars passing at the zenith, yeah, will cast a trajectory which is a branch of a hyperbola. Yeah, so it's a complex trajectory. So of course, with your detector, yeah, if the stars, yeah, are well tracing well one branch of a hyperbola, it would be very difficult to take an image. Yeah? So the first thing you would like is to linearize this trajectory to make it straight. Yeah? And for that, well, it has been possible. So Polikson and Richardson, yeah, have designed an optical corrector, yeah, which strengthens, yeah, the hyperbolic trajectory into a straight line. This is the first thing. Yeah. Now, well, this one I skipped. Yeah. I come to show you how to make at home your own liquid mirror telescope. Yeah? So it's very easy. Yeah. So first of all, yeah, you need a table that you may adjust horizontally. So I would take a piece of well, aluminum, yeah, with three small screws, yeah, which are shown here, 1, 2, 3, and you could adjust the screw so that the flat side, yeah, of your aluminum plate is perfectly horizontal. Then, well, here in this case we were using an old gramophone, yeah. So the rotational velocity will be 33 turns per minute, which means that the focal length will be about 60 centimeter in this case. So now we take a pie dish, yeah, and inside the pie dish, yeah, we just put some oil of a motor, a car motor, yeah. And then, well, at the distance of the focal plane, some butter paper, and then, well, you could directly see the image of the source of light, yeah, which is just above it. Now we showed this experiment, yeah, which was made by T.S. Kumar, by Pranchu Kumar, and by Surdej. I forgot his name, it's better, yeah, in Delhi when we had the visit, yeah, of one of our princes from Belgium, yeah. So what you see here is a gramophone, well, a more recent model, then the pie dish, then well, a camera, well, it's just a webcam, yeah, connected here to two screens, yeah. And then, well, the source of light was a slide with a picture of a well-known person in Belgium. Yeah. And then, well, the students were supposed to project the images on the screen. And when we were in trouble during 1 minute, but the image was the picture of the princess. Yeah. And so you see that even with the oil, yeah, from a car motor, you can do very nice things, and you could use such a small telescope, yeah, to catch images of stars, yeah. Well, if you place your experiment under the sky, of course. Here are our two Surdej in Pranchu. Okay, TDI mode of observation. So as I said before, yeah, what happens is that now we have a corrector. Now the trajectory of the stars are straight lines. Yeah? So what we are doing, we are shifting, in fact, the electronic charges there of the CCD detector at the same rate as the diurnal motion of the stars. Yeah? And then we are reading, yeah, well, the columns, of course, at a very high speed. And at the end of the night, what you're getting a very long movie of the sky passing over the zenith. Okay, now what is very nice about this technique of observation is that from the observations themselves, yeah, you can construct a very, very good flat field. Yeah. So here I show a raw images taken with that technique, and where you see there are lines which are not very nice. So what we do, yeah, we just calculate a median of all those columns, right? And we end up with something which is a one-dimensional flat field. But you see the value here is 1400. So what we do, we normalize it. We divide it by 1400. This is what you obtain. Then you replicate the flat field, yeah? Well, in a 2D CCD frame. This is what you obtain. This is a flat field, yeah, two-dimensional. And now you divide, yeah, your original image by that flat field. And what you obtain, yeah, well, you see here the difference between the raw image, yeah, and the flat field corrected, yeah. And in fact, the best well, source of light you can use to build up a flat field when you do observation of very faint objects, yeah, is a light from the sky itself, yeah. So it's exactly what we are doing, yeah. Now I like to show here the picture of Professor Joshi, and then well, who has been a big support during the time of our project. Also Professor Govind Swarup, who both have been the president of the governing council of ARIES. Yeah? And in spite of many obstacles, administrative obstacles that we faced, yeah, they helped us a lot. Yeah? So I like to remember them. Yeah. Okay, now I come to the 4-meter ILMT. So it's a very simple telescope, yeah, the most simple you may think of, yeah. And I think simplicity, yeah, always leads to quality, yeah, of the data you're handing up, yeah. So it's made of a main structure, you see, which is non-movable, so it's very cheap, yeah, very stable. Then you have the top hand, yeah, upper hand with a optical corrector, well, alignment mechanism, of course, and the CCD camera. And then you have the main mirror, yeah, with the recipient sitting on a hair bearing with a central motor and just a 3-point mount, yeah, to adjust well vertically the optical axis of the mirror. Now here is a small video showing different steps when we made, you know, the mirror. So here we are preparing the resin that will make the spin cast of the mirror. So at the beginning, yeah, the cylinder is made of very thin sheets of carbon fiber. And now, where you see people, we will pour the liquid resin on the recipient that is in rotation with a good speed, yeah, which is about 8 turns per minute. Then typically it took half an hour for the liquid resin to get solidified. And then the surface you obtain, yeah, is that of a paraboloid, which is good within a fraction of a millimeter. So this is not of optical quality, right? And it's just after, well, getting this solidified that you may start pouring inside some mercury as a, well, very thin coating. Yeah? So typically we are pouring 50 liters of mercury, but given the density of mercury, 13.6 kilogram per liter, well, the total weight is something like 600 kilograms. And now you see how we start spreading the mercury on the mirror by just acceleration, deceleration, because at times where the superficial tensions are very, very high, very strong, and there will be formation of holes. So we will see in a moment. So you see holes, yeah? And to get rid of those holes, yeah, you just need to change regularly, you know, the acceleration, deceleration. Then when we see no more holes, yeah, well, the central motor, yeah, is turned on. And then in our case now, we started spinning the mirror on October 6th, yeah? And so today we are 2nd of April. It didn't stop yet, yeah? It's still running. Okay, now you see that the shipping of the liquid mirror started in 2011, yeah? So here is a packing at Amos in Liege, then set up, yeah, on a big truck. Then it went on a boat, yeah, well, crossed the oceans and arrived, yeah, here. So this is transportation, well, at Devastal. Now transportation of the mirror separately, with a big worry at the moment because the mirror fell down on the street, yeah, on the way, but nothing happened really. Now, well, the dome is something very simple too. You have only one movable part, yeah, which is the roof, as you see it here. So it's very inexpensive because you don't need to rotate, yeah, the dome. You see here different phases during the construction of the mirror. So my spouse and myself were very frightened, yeah, when we saw where those engine workers working on the structure because they were not secured at all, yeah. And then at the moment, yeah, I really got worried. Well, Anna made that picture. I was really worried. Then I contacted the ARIES engineer and said, well, you know, it's dangerous. Yeah, do something. He said, no. Then, well, here they lifted, yeah, a 1 ton, yeah, a beam on top of it, and suddenly, yeah, the beam fell down. Oh, 1 ton, yeah, and then the structure, you know, shaked. And when the workers, you were hanged and nothing happened, but really it was dangerous. Yeah? So here you see, well, evolution of the structure. Now I like to show, yeah, all those courageous men, yeah, who are participating to the erection of the structure. Also digging hole, yeah, to find a good earth grounding, yeah. So these holes here were, I think, 7 meters deep, yeah. And it was fantastic, yeah. And, then we were thinking, yes, we are not all equal, yeah, and let's try, yeah, during our life, yeah, to make men, yeah, as equal as possible, yeah, sure. This is our role, yeah. Now, well, erection of the mechanical structure of the telescope only took place in 2017, yeah, so a long time after. Okay, well, you see here the dome, and then the control room here, and here is the compressor room. I will come to that point in a moment. Now, this is a liquid mirror telescope as it looks today, yeah. So we have here a big tank where the mercury is stored. And then where we have a pumping system, yeah, to transport the mercury to the center of the mirror. Here is a side view of the mirror. Then the air bearing system, so which is acting, you know, under very high pressure, compressed pressure. Then we have a very good UPS system, yeah. And yeah, I should say that we were very lucky when Professor Dipankar Banerjee, yeah, became the director, because when he was after Professor Dipankar, the first director who was supporting our project, yeah, very strongly. So still the UPS. Then we have a two compressor system, yeah, to make sure that if any of these, yeah, has a failure, yeah, the second system, yeah, comes into action. So you see two big air tanks. And then we have some air filtration system, just to get rid of oil, moisture in the air, yeah. Also dust particles in the air, which would put in a severe danger, you know, the air bearing system. Okay, here you see a view of the optical corrector, which is hanging, yeah, about 8 meters above the mirror. And it's a very complex system because it consists of 6 lenses, yeah, some of which are set off axis and slightly inclined to make sure that the hyperbolic trajectory, yeah, gets straight. Now, when AMOS came into play, they say, well, we have no experience and we don't know how to install such a corrector, especially that you must orient it perfectly within 1 degree along the south-north direction, yeah. But then with all the bright people, yeah, we have in the team, yeah, it's the idea to hang, you know, a pendulum here. And we said at the local noon, yeah, the pendulum should cast on the corrector, yeah, a shadow oriented perfectly north-south. Yeah? And it's what you see here. Kushal, one of our technicians, yeah, making sure that he's orienting the corrector at local noon, yeah, making it parallel, yeah, to the shadow that you see here. Here's the shadow of the pendulum. Yeah. Well, then you need an interface between the optical corrector and the camera, something quite complex with alignment systems. And when it arrived the first time in Devastal, it was all broken, all pieces, yeah, it fall down, yeah. Because during transportation on the Indian road, you know, yeah, well, the trucks didn't pay sufficient attention, and so it was a disaster. So it was sent back to Belgium, yeah, and it came, well, and then Hitesh, our mechanical technicians, yeah, accompanied the driver, yeah, and every time you would see something, slow down, yeah, so it arrived, you know, full. Now here what you see is a CCD detector, so it's a 4K by 4K, cooled down to a temperature of minus 110 degrees Celsius to make sure that dark noise, yeah, is the lowest level it can. We are using basically 3 filters, which are the Sloan filters, G, R, and I bands. Here you see the filter installed just below the CCD camera. It's a prime focus. Now, well, before pouring the mercury, yeah, well, the deep cleaning of the mirror is always made, yeah, by our technicians, yeah. So we are using isopropanol, yeah, to clean the mirror, and then we have special vacuum cleaner, yeah, to take all the contaminated material, yeah, in a safe way. Yeah. Now, one more thing is that when the mirror is spinning, there is some friction between the air and the mercury, and this induces ripples on the surface of the mirror. Yeah? So to get rid of this, yeah, we are making use, yeah, of a very thin mylar film 2.3 micron in thickness, yeah, of optical quality. Well, if you look, there is a loss, yeah, in doing that. We are losing 0.4 magnitude. So instead of reaching 22.4 magnitude in one scan, we are limited to 27 magnitude. Yeah? This is the only loss. Yeah? You see here the sheets of VAJRA, yeah? Just a line above the mirror. This is an aerial view of the mirror. And here you see, well, in real time, yeah, how it is working. Yeah? And so the first light, yeah, was obtained, yeah, in well, 3 years ago, yeah, almost 3 years ago. So well, there were many obstacles because at the moment, yeah, when we tried 1 year earlier to close the surface of Mercury, we could not succeed. And then we realized that EMOS, yeah, well, you know, who tried to make the best wind they could, it sent us, you know, the minimum quantity of mercury that was necessary. So we were missing just 5 liters. Yeah. So, okay, now one concern about the toxicity of the mercury vapors. Yeah. So what we did, yeah, just at the center of the mylar, we made a square hole, and there we were just pumping, I mean, the mercury vapors and neutralizing them, yeah, in a big container, yeah, where you have some charcoal inside, yeah. And it has proven to be extremely efficient because this is a recording of the mercury vapor content, yeah, during the formation of the mirror. And well, dangerosity would come up, yeah, when the level of mercury would reach number 27, yeah? But still at number 27, you could still work without a mask during 8 hours a day and 7 days a week. So, I mean, there was no danger at all. Okay, then sometimes there are celebrations, of course, yeah? So we invite PhD students, yeah, to spend a nice time. Well, of course, there have been many celebrations already. Now, this is a direct view, yeah, of the Devastal Observatory. You see here 1.3 meter telescope, yeah, with the dome totally open. Here is a 3.6 meter DOT and the 4 meter ILMT just here. Now, Devastal is a very nice site, yeah, not only good for the seeing, but also for sightseeing during the day. You see when there is no moisture, yeah, you may see Himalaya, especially during winter time, yeah. It's very impressive. Well, the nature is very, very nice, many nice birds, you know, butterflies, etc. Sometimes harsh conditions. Here is an evacuation, yeah, forced evacuation in 2019, when people had to walk about 15 kilometers, yeah, with luggages, yeah. Okay, here is another view. It's a birded vulture, you know. And just in front of the control room, there is a rocky, well, a rocky place area. So these birds just come with their prey, yeah. And at a very high altitude, yeah, they just let the prey fall down on the, well, there are many bones, yeah, on the ground. They try to crush it, and then they are hitting, you know, well, what is inside, yeah. Okay, now science with ILMT. Well, universe isn't coming to an end. You just let the cap on. So this kind of situation happens very often during observation. You know, something doesn't work, you don't know why, and then there is stupid well, reason for that always. Now, what is shown here, yeah, is a path of the field of view of the ILMT projected here on the representation of our Milky Way. So you see that we passed twice in the Milky Way, but that we also reach very high galactic latitudes, yeah, which is very good for, let's say, extragalactic observations. Yeah. Here, a nice picture, yeah, that has been made, yeah, by Sarat Prabhu, who is sitting there, yeah, when he was project associate, I think, yeah, in Devastal, yeah. So you see, when things are true, the Milky Way pass just over the ILMT, yeah. Well, now, just a few pictures, yeah, of the sky as we are collecting, yeah. Here you see a nice open cluster, yeah. So easy to make color images, yeah, because you're observing in G or I bands. Yeah. Well, here, detection of a nice planetary nebulae, and then another known one, NGC 2371. You see three conspicuous. Unfortunately, yeah, too many space debris, but those are of interest for space organizations. Yeah, so we hate them, but we also like them. Yeah? Well, here you see we are detecting extremely many minor planets. Here you see one observed during 7 consecutive nights, yeah, when spacing space debris. Then, well, sometimes strange objects. Now, if we play with dynamics, well, we see, oh, nice case of interacting galaxies. Yeah? Then, given the very wide aperture of the ILMT, so F2D equal 2.3, it's extremely good to detect, let's say, diffuse extended objects. So here you see different types of gaseous nebulae, well, diffuse nebulae, reflection nebulae, gaseous nebulae. Well, here is an example of gaseous nebulae. You see very nice structures. And right now, well, most of our time here, we devote to the detection of transients. Yeah. Well, this was a first detection of a supernova here with the ILMT. Oh, here, yeah, I just show one. We detected on 19th of March. Yeah. So this is, well, every day, yeah, we get about 100, let's say, 100 cases of transients. And, well, this is one example here. You see an image obtained during the night, and this is a reference image. Now the result of subtracting this one from the left one gives you this idea. So you detect variable objects, yeah? And in this case, well, it's a supernova, yeah? Detected here. No conclusions. Well, the ILMT is an instrument entirely dedicated to survey, yeah, photometric and astrometric survey. So the astrometric precision, yeah, is better than 1/10 of a second of arc, yeah, 1/10 of a second of arc. And well, the mirror quality is limited by the diffraction, and we are essentially limited by the median seeing, yeah, which is something about 1.2 second of arc. Now, well, the advantages is that observing at the zenith provides you the best image quality you may expect during the whole night. Yeah, where transparency is also the best there. Yeah, in light pollution the least. Yeah. Well, it's relatively cheap. Yeah, where the typical cost of a liquid mirror compared to the cost of a glass mirror of the same size is a factor 50. Yeah, so you could get 50 liquid mirrors for the price of one glass mirror. But of course, you cannot orient our mirror. But still, if you would like to enlarge the field of view, the Marseille people at that time had the idea to use well, off-axis optical correctors. Yeah? So the optical corrector would be set off-axis, yeah? So not over the mirror. And you could put as many as you want, yeah? But it would represent the cost, of course, yeah? But you could enlarge significantly your field of view. And now, of course, we are just integrating during a time of 1 or 2 seconds, yeah? So a little more than 1 minute. And essentially what we do, when you have 2 images, or you make the difference between the two, if nothing happens, you find 0, 0 everywhere. But anything which is new, you detect immediately. And that's what we also do. We are just co-adding all images here. So having a gain in magnitude as the time goes on. Yeah. Now, well, I would like to show you how images looks like in Devastal 6 years ago. But it should still be the same about today. Well, you see Orion Nebulae, well, Orion constellation here. And then, well, the lights are a bit, could you switch off the lights? Yeah. Yeah. It will help, yeah. Yeah. Okay, thank you very much. Yeah. Well, you see some serious passing cloud. Well, this is Saturn at that time. And here we have the Scorpion constellation. Yeah, with this is Antares, yeah. And here a galactic center, yeah, the tail of the scorpion. But you see that well, it's a very nice site where you may get very, very nice data. Now, we may also observe very nice sunsets, yeah? So we also like the sun, just like the Beatles, who have written a very nice poem, yeah? But the fool on the hill sees the sun going down, and the eyes in his head sees the world spinning around, yeah? Very nice. Where there is a nearby temple, yeah? About maybe 50 meters from the OT. So it's a very romantic site. And here is a nice view, yeah, where you see what I was telling before. If you look at the intersection of a cone with a plane, what you see for the equatorial star, you see a straight line. And for the star which are non-equatorial, you see branches of hyperbola on one side or on the other side. Yeah. So thank you.
Yeah, first of all, I'd like to thank Joe for this. I think he's an ideal example of how to enjoy the nature, and science is part of it, you know. I must say, you know, there is a connection of IST with him. He has not explicitly mentioned it. Those who are in masters in astronomy, astrophysics, the first batch of MS student, Vikram Pradhan, after finishing his masters, he did his PhD from Belgium. And then we hired him as a postdoc at ARIES, but within 6 months, he was absorbed in ISRO. So he is a mean person who is actually working for the SSA program. Of course, you know, there are senior members, but the hardcore work is done by actually Vikram. And Vikram worked on ILMT, worked on SSA under John. You can see that he enjoyed his time as well. And also this other student in that same batch is now a faculty at ARIES as well. So the MS program of astronomy, Govind. So Govind is the other person, Vikram's batchmate. He is a faculty at ARIES. We hired him very recently. He did his PhD from France as well. So yeah, I mean, this is really super. And I also must point out that these kind of programs are successful because of collaborative effort of real scientists with industry. This is again another very clear example. You saw from John, he's a leading expert in, you know, many astronomical, top level science output, and he worked in ESO, that is the top level observatory of the world. He has first-hand experience of being in the observatory and then in teaching, then building next generation. But while building this instrument, you saw from the pictures that he had been involved on a day-to-day when the telescope was built. And I can tell you that telescope of 4-meter liquid mirror telescope is actually at a lower cost than what is there in 1-meter Punmudi, I understand. So we still do not have any operation of Punmudi, but this is again another example of how it is important for the scientists, the students to participate in this kind of major project, which is technically very challenging as well. It's not that, it's you just hand over the drawing to the, industry and they will be able to make it. They will never be able to make it because it needs a lot of innovation and research. The other thing, John and Anna was actually living in a small little room when ILMT was getting, even constructed. So first observation started, we have guest house, which is slightly, in the foothill, sort of the base camp, which is difficult to commute in the night and so on. With the night sky gets clear, they just wake up and start observing. So it's a small little room, even cannot accommodate 2 beds. They were they were sleeping on the floor. I've seen, and so the kind of dedication a scientist can, have, it's really salute, sir. So I think it's a time for questions. Yeah.
Yeah, I'm always referring to that flat that we were occupying. It was exactly 10 square meter. It's a five-star hotel. The reason was that sometimes when there was no moisture, we could see the Himalaya, 180 degree, yeah. So it was unique, yeah. So we're just enjoying. Yeah.
So you have to know how to enjoy.
Yeah, yeah. Then one thing I would like to add, yeah, is that the purpose of my visit here, yeah, is really to start thinking about how to promote the mobility of PhD students, postdoc, also the staff members, yeah, between Belgium and India, yeah. So this is one reason, and another reason is to try to start interesting collaborative projects, yeah. And then also, well, what we would like to organize, yeah, is a contest, yeah, for probably PhD, maybe postdoc levels too, yeah, which would be the following, yeah. Well, regarding ILMT, for instance, yeah, you know, we are detecting space debris streaks, yeah, and the really luminous ones, you see them with your eyes. Now there exists already, you know, algorithm easily available on the web, yeah, which you could use to retrieve these, yeah. But what they cannot retrieve are the very, very faintest ones which are not visible to the eye. So the contest would be, for instance, was the best project, yeah, on detection of invisible streaks on our ILMT frames. Yeah. Well, another well possible project would be, for instance, could you think of another liquid, yeah, than mercury to be used in liquid mirror, yeah? Which, if it would be the case, yeah, I know that it would be easily possible to find the funds, yeah, to construct at least a 6 meter, yeah, in India, liquid mirror, well, using non-mercury, because people are frightened of the toxicity, and one has to be very extremely careful when handling that. And the only person who had a very good experience with that was Professor Polixon, who trained us, yeah. So we learned from him, but well, we would like to get rid of that liquid, yeah, yeah. And tomorrow I will still say, yeah, that another possible example of a project could be the identification of multiple image quasars in the ILMT archive of data here. And tomorrow I'll make a presentation on gravitational lensing, so I can already give some clue.
Yeah, tomorrow's talk will be a little more technical, and you can really see, you know, how. The other thing which he briefly mentioned, you know, again, ILMT data is a real the real example of AI/ML. So the machine learning is heavily now required for identifying these objects from these huge data which you know, ILMT is acquiring on a daily basis.
Yeah.
And in 5 years, it will have, you know, tons of data to work on.
Yeah, and then what I forgot to mention is that the prize of the contest, yeah, for the winning team, would be participation to the total solar eclipse in Europe in 2026 or 2027, because there will be two. Yeah, yeah. So
attractive things for participating. Yeah, Ananda, the first question.
Thank you for a wonderful talk. I just had a couple of questions. So during an observing season, this mirror is constantly kept rotating, or on every night it is switched on and
constantly rotating. We never stop the mirror.
So it's always rotating.
Yes.
Okay. And the other was the mylar sheet, which you mentioned. That was which is laid on top. That is to contain the mercury vapors, or does it serve some other?
To avoid friction between the air and the mercury, that would injure the formation of ripples on top of the surface of the mercury. But now, what is also very nice is that on the mylar, you know, dust, yeah, is falling down, yeah. And so from time to time, we are blowing air, compressed air, and just getting rid of the
So this
dust.
is transparent mylar sheet.
Yeah, it's transparent mylar sheet. Yeah, absolutely. Yeah, and so well, the mirror is always clean. Yeah.
And one last question is, I think you briefly alluded to this. Since the viewing is more or less confined to the zenith, so how do you make full use of the field of view? I mean, in terms of the off-axis aberrations that would come in, are there any corrective optics?
Yes, no, it's just where the optical corrector I showed, yeah, with 6 lenses, yeah, correct for all those aberrations, including, yeah, the curvature of the trajectories, of the stellar trajectories.
So they are just above the mirror. These off-axis mirrors are.
Yes.
These corrector mirrors are kept.
Yes, absolutely. Yeah, it's a prime focus. Yeah, it's a prime focus. Yeah.
Okay.
Before the camera. Yeah. Yeah.
Thank you.
Yeah.
Would it be possible to make like some kind of liquid mirror telescope where instead of rotating the liquid, we use some magnetically and rotate magnets around it?
Yeah. So people already looked into that problem, yeah, and it should be feasible, but very expensive technology would be needed, yeah, and probably too expensive that is not being made yet, yeah. Well, they made it on a small scale, yeah, very small scale, but once they want to extend it, it becomes prohibitively expensive, yeah. Yeah.
Thank you.
Yeah.
Yeah, while just using this rotation of this mercury, so after making this mirror, suppose there are some defects in some kind of area, how will we actually rectify it? If suppose we are noticing at the last stage of rotation.
Well, so you mean that on the polyurethane, there could be some defect, yeah?
Yeah.
Yep. Well, the mercury will just fill the holes, yeah? Yeah, naturally. And there were defects, of course, yeah. Yeah.
Younger people should have more queries, yeah.
Is it important for it to be a liquid mirror, or can we do something where we freeze some liquid in a parabolic shape and then we don't have to use liquid anymore?
You mean, would it be possible to think about something else than liquid?
Like we rotate it, and once it gets the shape of a parabola, we freeze it like that
Yeah,
somehow.
I see. Well, I understand your point, yeah. The problem is that there would be a problem with phase transitions at the moment that it would get solidified, yeah? And then you would have some ruptures, yeah? It's what you observe with ice, with anything, So it doesn't work. Otherwise, yeah, there would be some possibilities, I agree, to do that, but it won't work because of the phase transition problems, which are well known, yeah? Yeah, it's a pity, yeah?
Sir, I wanted to ask that given the diameter of the liquid mirror telescope, since we are using a liquid mirror, so we cannot use any kind of adaptive optics to correct for seeing. So at the current stage, given the current diameter, does it pose a large problem, or will that be a problem that will be faced by using only when using a much larger liquid mirror?
No. I think I don't see really the interest of using adaptive optics. Well, adaptive optics would be for a very narrow field. You agree, yeah? First of all, yeah. And then the stars are moving, yeah. So what you would need, yeah, is a laser guide star, yeah, that is moving during 1 or 2 seconds, yeah. And I don't think there is any good use of a liquid mirror to do that kind of experiment, yeah? Because you will need, well, all the adaptive optics systems, the laser and you could only look at the star passing near the zenith, yeah? So it's very limited, it's too limited, yeah? Yeah.
Thank you.
Well, people looked at the possibility already, yeah, to install such a liquid mirror telescope on the moon, yeah? So I mean, and where the gravity is less, yeah. So I mean, well, and the rotation of the moon is also slower. Yeah, you could look. Well, it was Roger Angel, who had a paper published in Nature on such a feasibility. Because while constructing a liquid mirror telescope is much easier than transporting, a glass mirror, yeah, which would be, well, horribly expensive. Yeah.
Yeah, it's primarily the cost for a large field of view. Adaptive optics and all that, as you pointed out, is good for single object tracking and all that. Here, millions of objects is
Yeah.
captured in one frame. So that's what is most important part. Yeah, so as it mentioned, Joy is here for next 3 days almost. So students who are feeling shy to ask questions, feel free to drop by his office. He's a very friendly person. I can guarantee you. You will not have any hesitation when you meet.
Don't be afraid.
Here. So if there are no further questions, let me hand over to Samir again for final words.
Fais-toi.
Okay, thank you, Professor Dipankar, for basically elaborating the discussion and the question session. Now, it was a wonderful lecture. So we are at the end of the lecture, but before we close today's session, I request the Director IIST to hand over a token of appreciation to Professor Jean.
Oh, what's that? Fantastic. It's impressive, yeah? Yeah, yeah. Pictures. Thank you so much. Yeah, it's so nice. Yeah. Yeah. So I take it directly in the plane with me, Yes, very nice. Yeah. So this is a launcher, yeah, of
This is
that was used
the
for
best one which we have.
that you have used now for probattery and.
No, that's actually
No.
PSLV. So this is GSLV.
Oh yes, yes.
It's for the bigger missions.
Bigger missions, yeah. Very nice. Thank you so much. Yeah. Wonderful. Thanks.
And before I disperse, I'm going to send another email for tomorrow's seminar. So that will be more on astronomy related stuff at 3 p.m. D2 building, classroom number 305. I'm going to circulate an email today itself. Thank you all.